Okay, kids, I realized I did things kind of out of order. Usually I make the angle of elevation thing from 8.5, the video after the quiz, and I do this before the quiz. Messed that up this year, so here you go. Here's your video on law of sines and law of cosines, 8.6. All right, so far we've only used sine, cosine, tangent in right triangles, and now we're going to expand that a little bit to be about more than just that. Notice it says any triangle just about. There's a couple little caveats here. Okay, here's the law of sines. Some of you have been using this already, either appropriately or inappropriately, but you know about this, most of you. Anyway, here's the law of sines officially for the first time. In any triangle, so this doesn't just have to be a right triangle anymore, but in any triangle, if we label these things as, if it's triangle ABC, and notice how they carefully label the length A opposite the side A, and B is opposite B, and C is opposite C. Notice how this is true. The sine of A over A equals the sine of B over B equals the sine of C over C, and that's quite remarkable. So again, this applies to all triangles, not just right triangles, but let's just be careful here. Notice what this says here. This is helpful when you have at least one of those fractions completely known. So if you have an angle and a side opposite it, you can fill out one of these fractions, and if you know anything else, like one of these other things, you can find the other thing. But be careful. If what we're given is angle side angle or angle angle side, we're fine because we know that those triangles are unique. Like those are congruence. Sorry, triangle congruence theorems or postulates, so we're fine. But if what you know is SSA, it gets a little bit tricky. So let's do some examples first before we get into the whole ASA versus AAS. Although I think what I can say right now, notice this, law of sines only works when we have blah or blah. If you have two angles, you can always trust law of sines. If you know two of the angles, well, essentially, if you know two of the angles, you know three of the angles. So if you know more angles than sides, we're going to do law of sines. And I say that because there's two laws today, law of sines and law of cosines. If it's all about knowing more angles, it's going to be law of sines. Take that to the bank. All right, so here's a couple problems. You've had this term solve a triangle before in the homework a little bit. If it says solve a triangle, sorry, kid interruption. If it says solve a triangle, it means find all of the lengths and all of the sides. So again, here we've got something we've never seen before. We've got some angles and some sides measured, and notice we have angle, angle, side here, so law of sines is perfectly fine. So let's set this up the way they say in the theorem. So the sine of some angle is over the side opposite. Well, I have the 78 and the 8 here, so I'll say sine 78 over 8 actually equals the sine of 60 over x. And I can solve that with the calculator pretty quickly. If I just rearrange the algebra, it turns into that, and in one step on the calculator, I get that. Pretty amazing. Let's do another one. Here's another one where I have angle, angle, side given, and I can find whatever I need after that. So the pair we have that goes together is the sine of 54 goes with 8, like, oh, we need this one. The sine of that thing will go with x. Well, that doesn't take long. 54 and 37. What did I say? 54 and 37. That's going to be 89. Oh, that's really close to a right triangle. 89. Then we can do this. If we just rearrange some of the algebra, and that gives us 6.473 in the calculator. So there's a couple examples where you're supposed to use law of sines. I noticed some people in the pretest were doing same kind of thing, using law of sines, even in SOHCAHTOA problems, and they'd have, like, if there was a right angle here, maybe, this is really close to right angle, they did right angles and they'd do things like sine of 90 over blah, blah, blah. I would encourage you to not do that. If it's a right triangle, you should use SOHCAHTOA, and we already know, I've already been saying that there is some kind of special cases where law of sines doesn't work, and actually, I'll say this too. People who were missing those problems on the pretest were people who were using law of sines. Yes, you can do it correctly if you're careful, but let's just use law of sines for when it's not a right triangle. All right. Here's some more law of sines stuff. We'll use the part that's opposite the... oh, sorry. This is angle side angle. That's a little bit different. So I can say sine of angle R over 6.8. I'll figure that in a second. Over 6.8 is going to equal sine of 125 over x. Okay, so what's angle R? All right, angle R is 31. So this is 31 in here. That's 31. So this is 31. Rearrange the algebra. And we get 6.8 times sine 125 over sine 31. And that is about 10.815. Okay, and this one again, we have angle side angle. So 14 is opposite this thing. We'll use that over 14. Sine of something, sine of angle t over 14 is going to need, okay, or is going to equal, sorry, x is going to go with sine 31. Oh, it's 31 again. Interesting. So that other angle is 86. And if we rearrange the algebra, we get that expression for x. So x is about 7.228. So notice in all of these, just like when we were doing the SOHCAHTOA problems, that the hypotenuse is supposed to be the longest side and things like that, we still remember those laws about triangles still hold, where it's like the opposite, the opposite angle is opposite the largest side. Sorry, the largest angle is opposite the largest side. The medium angle is up the medium side, that kind of thing. So if this is 6.8, we found out this is 10.815. That's good because 31 is a lot smaller than 125. And this one, we have this 14 that's opposite in 86. And x is a lot smaller. It's opposite of 31, so that's fine. Okay, law of cosines. Law of sines is only good when you know more angles. Law of cosines is good when you know more sides. So if you know like side, 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 or you know side, angle, side, we have a totally different rule because law of sines you may not have enough information to start law of sines. Okay, this looks a lot more complicated. I like to think of it as a modified Pythagorean theorem. Notice we have like c squared equals a squared plus b squared. A squared plus b squared equals c squared was the Pythagorean theorem, but it's got this slight modification when it's not a right angle. Again, because this is for all triangles, not just right triangles. The nice thing about this one is this works all the time. You don't have to worry about any loopholes or any kind of strange special situations where this isn't going to work. This is going to work all the time. That any side is going to equal, so like c squared is going to equal a squared plus b squared minus 2ab cosine c. This last version with the c squared by itself, this is usually the way you see it. All these are true, they just rearrange them. Notice the naming system is the same. A is opposite A, B is opposite B, and C is opposite C. So c squared equals a squared plus b squared minus 2 times the product of those two sides times the cosine of the angle. And notice this is a C here, and this is a C here. So this angle has to be describing the angle that's opposite the side here that's by itself in this equation. That's actually the main thing you have to keep track of, is that this side is opposite this angle. You're not going to mess up the other two if you get that figured out. Notice this is only going to kind of be helpful if we're given side, angle, side as the numbers that are in this triangle. They're already given. Or if we're given side, 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 actually we can use it to help find an angle. All right, so let's do some of these things. So here we have side, angle, side. We can use law of cosines to find the other angle. So this is going to be, so the C here, because you remember C was the only thing we had an angle listed for in the law of cosines. The only angle, and again, I'm going to keep talking about it in reference to this bottom one. The only angle involved in here is the angle that's opposite kind of the lone side that's on the other side. So here our C is going to be this 125 and this x. So we're going to use x squared as the thing by itself, because at the end it's going to end with cosine 125, equals 15 squared plus 19 squared minus 2 times 15 times 19. This gets to be pretty rhythmic once you get used to it, times the cosine of that 125. Now we've got a lot of simplifying to do. Let's simplify the numerical stuff first. And we can simplify it down to this. Notice we're getting some weird cosines here. Like this is cosine of the angle of 125, and you're probably thinking, hey, wait a second. I thought we were defining sine, cosine, tangent this year to just be angles and right triangles. And I think I said at the time, but just except for this one little thing. So in this section, we are going to start talking about angles that are bigger than 90 that might have a sine or a cosine. Just realize that yes, sine and cosine are defined for angles, actually for any angle, whether it's between 0 and 360 or even beyond that domain. And for now, we're just going to use the calculator as a magic button, kind of a magic machine, to spit out the cosine of 125. Don't worry about it so much right now. What the definition of cosine is for angles outside of acute angles, same with sine, because we can get some stuff from acute angles for sine and law of sines here, just from the last couple pages. Notice back here we had sine of 125. I didn't let it bother us then. I hope it didn't bother you. But yeah, it's possible that you can ask the calculator for the sine of 125. Some of these things might be negative. Again, don't let that bother you. It goes a little bit beyond our definition for this year, but for now, let's just go with it. Just realize that we can use it for law of sines and law of cosines, and we can talk about obtuse angles in these trig functions, and it's okay. All right, now let's go ahead and compute this. And maybe it helps to note that, yes, the calculator does this. It doesn't break. You can ask it for the cosine of 125. And we get a side of 912.939. Actually, I shouldn't say side. We get a value of 912.939. But realize that is x squared. So for x, we just take the square root of that, which is, just copy paste that in there. It's 30.215. And again, realize that in our triangle here, we have a 15 and a 19, and that side should be bigger. Good, yeah. But also realize that, 15 plus 19, this side can't be bigger than, 34 or whatever it is. But so this is a legal side for this triangle, and it should be longer than 19, so that's good. Okay, here's another one, exact same thing where we have side angle side, so let's set it up. Sorry, that was really hard to fit in the box there. Realize that 7 and 4 are the sides that kind of frame our thing here, and the 62 and the x are the parts that are opposite each other, so those are the parts that would be the c. 16x minus 2 times 7 times 4, that's 56. Cosine 62. Let me do some more. Whoops, 62. I'm going to use this off camera. So that's actually the best exact answer at this point. I could put a big square root over that, and that's the best exact answer. But if we solve on the calculator, I get 38.71 for the square. And notice I would never type that in as my thing I'm going to square root. I would take the square root. You can go square root of the answer. That's kind of nice to get 6.222, or you can just copy paste that. Okay, and again, notice that makes sense in this triangle, that this probably isn't the biggest angle in the triangle. It actually looks like B is, and X is something that looks like a reasonable side for the length of that triangle. Okay, a couple more of law of sines, but this, law of cosines, but this is about finding angles. Okay, so here, the angle and the side we have that are opposite that we care about are this x and this 1.9. So we're going to use that as the c here. So it's 1.3 squared plus 2.1 squared minus 2 times 1.3 times 2.1 cosine of the angle. So when this is all done, I'll be able to solve for this cosine x. At the end, I'm going to have to take a inverse cosine. All right, this is 5.46 cosine x. We get to this point, we're a little bit alarmed. On this side, we have negative 2.49 equals negative 5.46 cosine x. I guess that's not alarming, because when I divide both sides by negative, I'll get positive. So it's actually 0.456. And that's actually not surprising at this point, because we know cosine should be a value between 0 and 1. So now all I really have to do is just take the inverse cosine of that answer, and I get an angle degree, or an angle measure of 62.868. And that's the angle size. And that doesn't surprise us too much. It should kind of be the middle angle of that triangle, and 862 is perfectly reasonable for that. All right, and the next one, again, we're going to set this up so that the 3 and the x are the c in this case, the sides that are opposite each other. So, or sorry, the side and the angle. So the 3 goes here and the x goes here, and everything else goes in as such. And that solves as such. 28.031 is what it says at the bottom there. Hard to read. Sorry, I'm making so many cuts. I want to get this done before 15 minutes of video is up. Next in your notes is actually the law of sines proof. I'm going to save this for another video. I'm thinking of other things I want to do in another video. But in general, though, I think it is important to realize this. If you have a right triangle, you should really be using SOHCAHTOA for these things. This is all basically SOHCAHTOA is what they're saying here. If it's any other triangle that's not a right triangle, then we start looking at things like law of sines and law of cosines. And basically, if you know more angles, be using law of sines, and if you know more sides, you should be using the law of cosines. All right, and then there's this huge discussion of how come, why is it that sometimes the law of sines doesn't work? I'm going to also put this in that other video. So bonus material in video 2.